Okay, so let's take a look at example 1. Here we're asked to use a triple integral to calculate the volume of a solid Q bounded by the graph of z equals 4 minus x squared minus y squared. So this is a paraboloid that has the vertex at the z coordinate 4 and opens downward like this, and we want to cap it on the bottom with the xy plane. So basically the solid Q being described here is sketched in this diagram here, right? So again, it's a upside down paraboloid where the vertex is located here. It opens downward and it's capped at the bottom with this disk in the xy plane. Okay, so before we set up the integral, we need to describe this region in cylindrical coordinates. So this equation here. So first, let's take a look at the region, the base of the solid, right? So in the xy plane, that means that z is equal to 0. So when z equals 0, as part of the paraboloid, we set it equal to 0. So you have 4 minus x squared minus y squared. And rewriting this, we can say that x squared plus y squared is equal to 4. Right, so this circle at the bottom here is basically just a circle of radius 2. Right, so the base is this circle plus the entire disk, right? So we should write it as x squared plus y squared is less than or equal to 4. And then switching to polar coordinates or cylindrical coordinates, x squared plus y squared is r squared. And writing in terms of r, this says that r is less than or equal to 2. Okay, so that describes this disk on the bottom. So now let's just put it together to describe the whole thing in cylindrical coordinates. Right, so the parameters r and theta are describing the xy plane, right, which is again exactly this disk here. So it's the full disk, so that means that theta should rotate completely around from 0 to 2 pi. And then r is already less than or equal to 2, right? So r goes between 0 and 2. And then now about the z coordinate, right? So the z coordinate should describe the top boundary and the bottom boundary. So the bottom boundary is the xy plane, right, which is z equals 0. And the top boundary is the paraboloid, which is 4 minus x squared minus y squared, but we want to write it in terms of polar coordinates, so that would be 4 minus r squared. Right, so when we're describing the z coordinate, again, that should be the top boundary and the bottom boundary, right? So this is the bottom, which is the xy plane, and this is the top, or the whole thing here is the top, which is the paraboloid. Okay, so this is the description in polar coordinates. So now we're ready to set up the triple integral, right? So we're trying to calculate the volume. And whenever you're trying to calculate the volume, you can think of it as the triple integral over the solid object and integrating the function 1. Okay, so this is how we calculate the volume. And so now we set up the triple integral. So theta goes from 0 to 2 pi. Then we do r next. So r goes from 0 to 2. Then we do z. So z goes from 0 to 4 minus r squared. And again, the function is 1, but then I have to multiply by r because of the dv, right? So dv is equal to r dz dr d theta. Right, so we have the r, and then dz, dr, d theta. Okay, so we need to integrate this. So what do we have? Integral from 0 to 2 pi, integral from 0 to 2, and the antiderivative of r with respect to z, right? So here we're thinking of r as a constant. So that would be r times z, evaluated from 0 to 4 minus r squared, and then dr d theta. And then let's evaluate this. So 0 to 2 pi stays the same, 0 to 2 stays the same, right? So now we have to plug this in for z. So we have r times 4 minus r squared, dr d theta. Let's distribute this so that it's easier to work with. So this is 4r minus r cubed, dr d theta. Okay, so now we integrate with respect to r. And also notice that the whole inner integral doesn't depend on theta. So what I can do is I can separate the theta and the r, right? So so I can actually write this as integral from 0 to 2 pi d theta and calculate that separately. Again, you can only do this when this integral doesn't depend on that theta here and also in the as part of the integral. And okay, so then integral from 0 to 2, 4r minus r cubed dr. Okay, so this is just the length of the interval, which is 2 pi. And then here the antiderivative is 4r squared minus r to the 4th over 4, evaluated from 0 to 2. And then now we just plug in 2, right? So 2 squared is 4, 4 times 4 is 16. And here this is 16 oh, I made a mistake here. So this 4r squared, so the antiderivative should have been 4r squared over 2. Okay, so now let's calculate, right? So when you plug in r equals 2, what is that? 4 times 4 is 16. 16 divided by 2 is 8. And then here, 2 to the 4th is 16. 16 divided by 4 is 4. And when you plug in 0, everything is 0. Okay, so then this is just 4 times 2 pi, which is equal to 8 pi. Okay, so so in this example, we first describe the region in terms of cylindrical coordinates. And so you can notice here the description is fairly straightforward using cylindrical coordinates. And then we calculated the triple integral that calculates the volume.